In this video, we're going to start off talking about equilibrium and reversible reactions. We're going to talk about it very generally in this video. Then in subsequent videos, we'll get much more detailed about how we can quantitatively deal. So let's go back to talking about concentration versus time for a reaction. In this reaction, methane and oxygen are reacting to form CO2 and H2O. And if we track the concentrations of CH4, the methane, and the O2 over time, they'll start out high and then they'll go down to some lower and lower value as time proceeds. If we also look at what's going to happen with the concentration of CO2, that's going to start out at nothing before any of it is created, and then its concentration is going to rise over time, and the same thing is going to be true for H2O. And of course, from studying kinetics a bit ago, we recognize that the rate of production of water is going to be higher than the rate of production of CO2, and the rate of consumption of O2 is going to be higher than the rate of consumption of methane. This is a reaction that will just keep going until we just run out of O2 or CH4. But there are some reactions that are reversible reactions, and those reactions will start to run in the opposite direction at some point. And in the next couple of units of AP Chemistry, we're going to be focusing on those kinds of reactions and how we can make predictions about their behavior. I think the easiest way to start thinking about reversible reactions is to just look at a generic reaction that's not really a real reaction. So here we have a reaction of a compound, AB, 2 moles of it, that are going to decompose into 2 elements that are diatomic, A2 and B2. So this is a little microscopic picture of our starting point. You can see that we have only AB. Let's say B is the blue dots, A is the red dots. So AB is a molecule that's a red dot and a blue dot. And we can see that we have 10 ABs at the starting point in our little microscopic sample that we're looking at. So if we're going to plot that, we could put a 10 here. And we don't have any A2 or any B2. And so, if this is 0 down here, that's what those concentrations would be at the beginning. Now we let the reaction proceed for a while. And now we can see that reaction has gone forward a little bit because we now have 1, 2, 3, 4, 5, 6 ABs. And we now have 2 B2s and we have 2 A2s. So we have produced some product at this point. And we have decreased the amount of AB that we have. So if we let the graph run, this is what that would look like. So 5 would be, about here. So we're at a little bit higher than 5 for concentration of AB, and we're quite a bit less than 5 still for concentration of B2 and A2. Okay, so we let some more time go on, and now we have reached a situation where we have 1, 2, 3, 4 ABs left. So that concentration has decreased, and we have now 3 A2s, and we have 3 B2s. If we let the graph play out, we can see that the concentration of AB has now dropped down below 5, and the concentration of A2 and B2 has gone up a little bit higher. Another thing that we see happening is that the curve is starting to flatten out, and that's understandable because as the concentration of AB decreases, the rate of its consumption is also going to decrease. Because remember, in our study of kinetics, we found out that with higher concentration comes a higher rate. So the forward reaction is slowing down. What we'll find out if we let the reaction go on a little bit more is that we have 1, 2, 3, 4. We still have 4 ABs. And we still have 3 A2s, and we still have 3 B2s. So what's happened is we've reached a kind of a flat spot on the curve. The concentrations of AB, A2, and B2 are not changing anymore. Now, it's important to note that this is not because the reaction has stopped happening. The reaction is still happening. What's happening is that the forward and the backwards rates are the same. So we're producing AB at the same rate that we're consuming AB. So that's why its concentration stays constant. And we're producing A2 and B2 at the same rate that we're consuming A2 and B2 for the reverse reaction. This is a period of the reaction that we call dynamic equilibrium, or just equilibrium for short. It's called dynamic equilibrium because the reaction is still happening. Equilibrium because it's happening at the same rate in both directions. Let's take note of where we ended up there when we were at dynamic equilibrium for concentrations, and just kind of keep that in mind. And let's look at another situation. Okay, here's another starting point. Let's say we start out with only A2 and B2. So here we've got 1, 2, 3, 4, 5 A2s, and we have 1, 2, 3, 4, 5 B2s as well. So this is 5 on our scale. And if this is 0, that's our concentration of AB. We don't have any of it. We allow the reaction to proceed a little bit. The reaction is going to go backwards because it can't go forwards. We don't have any AB to decompose. What's our situation now? We have 1, 2, 3. Now we have 4 A2s, 1, 2, 3, 4 B2s as well. And now we've got 2 ABs. Let the reaction go a little bit farther. And now we've got 1, 2, 3, 4 ABs. We've got 1, 2, 3 A2s, and we've got 3 B2s at this point. We let the reaction proceed a little bit more. We have 1, 2, 3, 4 ABs, 3 A2s, 3 B2s. So what's happened is we've reached dynamic equilibrium. The reaction is going forward and backwards at the same rate, and so we're not seeing any net increase or decrease in any of our reactants or products. We've reached dynamic equilibrium. And if you remember from the last starting point, we ended up at the same ending point. We had 4 ABs, 3 A2s, and 3 B2s when we reached dynamic equilibrium that time, and we did it again. Let's look at another situation. Here's a different starting point. Now we have some of each. We've got 1, 2, 3, 4, 5, 6, 7. We've got 8 ABs in here. We've got 1 B2, and we've got 1 A2. As the reaction proceeds, we see change in concentration. Now we've got 1, 2, 3, 4, 5, 6 ABs, and now we have 2 B2s, and we have 2 A2s. And this change is kind of predictable because for every 2 ABs that we lose in the stoichiometry, we're going to produce 1 A2 and 1 B2. So we went down by 2 ABs, and the count of A2 and B2 went up by 1 each. Now we're getting to that flat spot. We're getting to dynamic equilibrium. What do we have? 1, 2, 3, 4 ABs, 4 ABs, and 1, 2, 3 A2s, and 4 B2s. And as the reaction continues to proceed with that flat spot, now that we're at dynamic equilibrium, we still are going to have 4 ABs, 3 B2s, 3 A2s. So we always end up with that same ratio of particles in our little sphere here that we're looking at, no matter what our starting point was. We reach the same equilibrium. Let's take a look at a real reaction. And don't pay a whole lot of attention to the numbers at this point. We're going to get into this in a later video. But if we have this reversible reaction where 2 HIs decompose to H2 and I2, if our starting point is only HI and no H2 and no I2, this is what the concentration versus time graph would look like. And if we have the ability to track these, we'll find that at some point we're going to get a flat spot on the curve. So we've reached dynamic equilibrium at that point. If we start out with only H2 and I2 and no HI, like here we have 0 HI, but 0.3 moles per liter of H2 and I2, the H2 concentration is going to go down. I2 concentration is also going to go down. HI concentration is going to go up. And then we again are going to reach a flat spot here. Now one thing that you might notice here is that the concentration of H2 and I2 and the concentration of HI at dynamic equilibrium is not the same as it was in the previous example. Let's just slide back to that. Here we ended up with 0.16 molar HI, 0.02 and 0.02 for the H2 and I2. Here we end up with 0.48 and 0.06 and 0.06 for our concentrations. So unlike our particle example, when you're looking at actual concentrations, it's a little more complicated than that. But put that on the back burner for now. We'll come back to it later. Here's what happens if we start out with some of everything. We have 0.1 moles per liter of HI, H2, and I2. And the concentration of HI is going to go up in this case. The concentration of H2 and I2 are going to go down. So that means this reaction at first starts out going backwards faster than it's going forwards. But once again, we reach dynamic equilibrium. And once again, those are not the same numbers that we had in either of the first two examples. Now, there is something about the ratios of those numbers that is the same, and we'll talk about that later. But the key is that no matter where our starting point is, we do reach dynamic equilibrium at some point. Now let's think about rate rather than concentration. So on the vertical axis now, this is the rate of reaction, not the concentration. The reverse reaction is shown in purple, and the forward reaction is shown in blue. So this is the rate of the forward reaction at the top, the rate of the backwards reaction at the bottom, and when we reach dynamic equilibrium, it's not that we just have a flat spot. It's not that the concentrations are unchanging. It's that the rate of the forward reaction and the rate of the reverse reaction are exactly the same rate. So if we have the ability to track rate, this is what we would find. So that's kind of a confirmation that in this zone here, the reaction is still going on. The rate is not zero. The rate is some non-zero number. But it's the same for the forward reaction and for the backward reaction. That was for this first situation where we started out with pure HI. Here's for the second situation where we start out with pure H2 and I2. There's the rate of the reverse reaction. So that starts high and then goes down lower. And then this is the rate of the forward reaction. That starts out low and ends up being higher. And again, when we reach dynamic equilibrium, the rate is not zero, but the forward rate and the backward rate are the same. So at equilibrium, the forward rate equals the reverse rate, but neither of those is zero. How is it possible for the concentrations to stay the same while the rates are not zero? The answer is that product is formed and consumed at the same rate. Our next topic is to try to use particle pictures to predict the direction the reaction is going to move, forward or back. This is pretty common sense once you kind of go through an example. So this is the reaction that we're going to use. 2SO2 reacts with O2 to make 2SO3. Let's say that this particle picture represents equilibrium. Now let's see what we have here. If we count up the SO2s, we have 1, 2. So we have 2SO2 at equilibrium in this amount of space. And then how about O2s? We got 1, 2, 3, 4, 5. 5 O2s. SO3s, we got 1, 2, 3, 4, 5, 6, 7 SO3. All right, so that's the equilibrium condition. Now here's a different reaction mixture. Let's examine this and see if we can predict which direction this reaction mixture is going to run. Is this going to go forward or is it going to go backwards? Let's make a count. SO2, let's see what we have. 1, 2, 3. We have 3 SO2s. Oxygen, we have 1, 2, 3, 4, 5, 6, 7. 7 O2s. SO3, 1, 2, 3, 4, 5. We have 6 SO3. Okay, at equilibrium, we had 2 SO2, we have too much. We had 5 O2, we have too much. We had 7 SO3, we have too little. So we need more product, SO3, and we need less SO2 and O2. So this reaction is going to go in the forward direction to produce more SO3 and use up some of the SO2 and O2. Here's another case. Which direction would this mixture run? Let's do our count here. So for SO2, what do we have? We have 1 SO2. Oxygen, 1, 2, 3. We have 3 O2s. SO3, we have 1, 2, 3, 4, 5, 6, 7, 8 SO3. In this case, we have more SO3 than we would have at equilibrium, 8 as opposed to 7. But we have fewer SO2s, 1 as opposed to 2, and O2s, 3 as opposed to 5, than we should have at equilibrium. So we need to use up some product and create more reactant to be at our equilibrium conditions. So this reaction is going to run to the left, and that will accomplish that objective. Okay, so these are pretty basic and straightforward. But in real life, of course, we can't see molecules, so we cannot make these counts. So we're going to have to rely on something that could be measured, and that's usually going to be concentration or pressure if they're gases. So that will be the next video.